All right.
Welcome everyone to the next IITE seminar, and it is my great pleasure to introduce Hanna Kokko from University of Mainz in Germany. As we know, life history, theory, and life history evolution can be quite intuitive or not, and we are hoping to learn something about that from Hanna today. So, Hanna, the floor is yours. Thank you.
Okay, thanks so much for this invitation. And I thought I will, maybe unusually for me, I will just talk about one single paper in this talk, because it's a bit of a complex story, and that gives me the time to go through all the details that are relevant there. And this is work that has been published. It's done by these fantastic two postdocs who are no longer in my lab. They fledged very successfully to their new adventures, Matthias Galipeau and Lotte de Vries. And also, this is interesting because I'm actually not saying anything particularly new. If you're somebody who works in this field, you might get the feeling that, oh, all these points have actually been made before. And I think that's true, but these points have been made in a way that makes it quite hard for new people who come into this field to understand what's actually going on, because there's so many papers, so many arguments and so on. So with this sort of slightly cryptic self-introduction to this project, I think I will just tell you what the question is here. So the question is, how would you deal with the, well, I'll just explain this cartoon. It comes with several different sections, but the first one here, from this fantastic cartoon, xkcd.com. This person has clearly done something fantastic, and there's this great booming voice coming from above saying that for saving my kingdom, I offer you a gift of great power. These magic shoes enable the wearer to outrun death itself. And then you open the box, and what happens is that there's these shoes that are these creepy, that have this sort of individual slots for each of your toes. But, you know, the advantage is that it makes you immortal. But then, of course, the disadvantage is that, you know, all your life you have to wear this and you look creepy and, you know, all that. So you have to think about this. So this is this question of how you should value this product is what I'm talking about in this talk. So what I'm redefining this thing here, it's about something that avoids you becoming ever senescent, meaning that you don't get these diseases that are associated with old age. Your mortality rate doesn't go up as you get older, but you don't actually become immortal, because you still suffer extrinsic mortality. So, for example, you might get run over by a bus and then you're dead, even if you're wearing these shoes. And all kinds of things that can happen to you, even though you're completely healthy and the beginning of the day, you're dead at the end of the day. It's actually interesting to think about how long would you live if this was the case. And this, of course, depends a bit on how dangerous is the society that you live in, and do you wear a seatbelt and all those kind of things. But generally, the sort of average, what people get in societies, you know, Western wealthy societies, this chance that you are healthy and alive in the morning, but by the end of the day, you're suddenly dead unexpectedly. It's about 1 micromort, which is short for 1 chance in a million. Some people react to this news by thinking, oh, that's actually terribly high. Some of them sort of categorize it a bit differently. But if you do the inverse of that, and realize that you're going to live on average about 1 million days, exponentially distributed, this would be something like a 2,700 year old lifespan. So clearly, you know, mostly we die of old age related things, rather than being run over by other kind of accidents. And that actually aligns quite well with intuition in modern Western wealthy societies. But the life history question, and where this becomes also sort of a thing about different kinds of organisms, is why do different organisms have such a different lifespan? So in other words, is there selection to invest in even trying to be a very long-lived creature that depends on what kind of environment you live in as an organism? So, for example, if I still keep the sort of human metaphor going here, if you lived in a super dangerous society where all kinds of reasons to die just happen to you, would that make you value these shoes less? So if there's this trade-off that makes it look ridiculous, and therefore maybe your mating success is low or things or not, depend on how dangerous the society is that you live in. So without making this a human question, George Williams, the famous evolution biologist, thought that there clearly should be covariation here. And this has become known as the Williams hypothesis. So if I now switch to this biological way of explaining it, if unavoidable mortality is high, you get predated upon, or like in the case of this colorful killifish that you see low down there, their habitats just disappear at the end of the season, then it clearly is intuitive that there's no point even trying to build a really, really robust body that lives potentially a long time, because this potential is never filled. Whereas the evidence that some of the individuals that are swimming around the ocean right now are hundreds of years old. So clearly they live in much more stable environments where you can actually reap the benefits of trying to delay senescence. So this link between extrinsic mortality and lifespan is the Williams hypothesis. So if I phrase this as a question, this has been such an intuitive prediction that it has been tested already quite a long time ago. This is an old paper where they looked at the idea that one way to lower the extrinsic mortality is to be able to fly away from your predators. So with this title, Fly Now, Die Later, they asked, if you are a thing that can fly or glide, then does your longevity, which always has to be scaled with body mass because this is a very well-known correlate, is it always above the line for the non-flying mammals? And it looks like for all the cases that they investigated, this seemed to be the case. And of course, bats should also be in this figure. They are not, but we do know that bats, which are also flying mammals, they are very long-lived for their size. It's a bit of a more complicated story than that, because they also get much longer lived if they hibernate. So it's almost like if you're asleep, then it doesn't count towards the aging processes, which also makes fairly intuitive sense. But yes, if you do take a bat versus a mouse, same body weight, then the bat will very likely be the long-lived, more long-lived organism. And of course, there's other taxa as well, some very good flyers out there. And I always like to tell this story, it's very cute. This is a particular individual albatross called Wisdom. Back then in 2021, she was 70. She was actually at least 70. And once again, she was breeding and hatching another chick for that year. And if you think about this, she's about the age of my mother, but my mother is certainly not producing babies every year. So this is quite phenomenal. And I kind of hate the moment when at some point I'll probably get the news that she didn't return to the breeding site. It must happen one of these years when I'm alive. But this is the latest that I found of her, that she once again in 22, she came back. I don't actually know what she's doing this year. And she might even be older than this. She already had adult plumage when she was banded in 1956. Which was actually a year before Williams produced his very classic theories about senescence. So sometimes investing in a very long lifespan can make sense. But if I think about this prediction that, like, obviously you need low extrinsic mortality for this even to be an option to delay senescence for so long, it looks like there's this huge, well, at least moderately sized literature where modelers seem to be fighting about whether this prediction even should be made. So there's this very funnily stated titles such as reports of the death of extrinsic mortality molding senescence have been greatly exaggerated, meaning that clearly somebody has been telling that this hypothesis is dead, and then somebody saying, no, we actually shouldn't call it dead. And what does this person write here? There's pointing out that there's a claim that the classic theory wouldn't predict an increase in the rate of senescence with an increasing extrinsic mortality. This is an incorrect claim. When we start assuming that there's a realistic, that there is a constant population size on an evolutionary time scale. So this guy was right, and empiricists have not been misguided when they try to test this. On the other hand, there's papers such as this one here, which is a bit more recent, where they say that, you know, we still should be very, very skeptical of the Williams hypothesis. And they talk about that paper saying that, well, this R equals 0, R here's now the population growth rate. This should somehow be specially relevant because populations over time must be on average not growing or shrinking. But then they say that, well, this is kind of not a particularly interesting case, because even if we consider R equals 0, we can build models, and then we once again find no effects on selection. And when they say, you know, this can happen with arbitrary growth rates, including 0, then this sounds like this is a very general model. But note that they actually make an assumption here as well. So they say that this is where the mortality that is applied is age independent. So I wouldn't blame anyone who tries to read all these things and think that, oh, this is all very confusing. How can I actually, for example, as an empiricist, make sense of what should I even be testing? So what we wanted to do is to really produce a as easy as possible way to unpack the entire set of arguments here. And whether you consider it easy or not, what follows here, it's quite a multi-step argumentation here. That probably depends a bit on what sort of person you are, but let's try. So to understand what the debate is about, we would first need to understand, why is it even possible to make this claim that there's no effect, even though the hypothesis sounds so intuitive? So for this, I have these two hypothetical organisms here. There's a mouse and there's a bat. And I'm making the assumption that they are exactly identical in their life history in all other ways than extrinsic mortality, where it's very high for the mouse. 80% of them die between each breeding attempt, including the juvenile period from being a newborn to trying to breed the first time. And let's put that as half as big for the bat. And it's a bit easier to work with survival. So just from one breeding attempt to the next, there's just 1 minus the extrinsic mortality. So it's 20% for the mouse and 60% for the bat. So the intuition that is inherent in the Williams hypothesis is that if we quantify how strong is selection to delay senescence, it should be weaker in the mouse and it should be stronger in the bat if we made a comparison. So this is what the hypothesis is all about. So if I just sort of said that, well, these are the rules of life, then there was actually no senescence in the model yet. To make the minimal model where these things also die because of old age, we are assuming that there's some sort of an intrinsic decay process. And let's just say that there's two different genotypes. It could be a rapidly senescing genotype. Then these individuals, if they manage to breed once, after that, they are already so worn out that they die. Whereas if it's a slow process, so this is the genotype that has a bit of a more robust built body, then they can breed twice, and after that, they are dead. So this is a very sort of caricature of the real cases, but it allows us to explain the argumentation in as simple ways as possible. And in a way, this is, of course, a sort of no-brainer, because there's no disadvantage of being a slow senescer. There's only an advantage, because you at least have the chance to build, to breed another time. But the point here is that we are trying to quantify the intuition that the bat is selected to delay more strongly its own death than the mouse is. So this is what we are trying to quantify. So let's figure out the expected number of times that a newborn mouse or bat will breed if it's a rapid senescer, so that it dies after breeding once, or if it's a slow senescer, so that it dies after breeding twice. So here, the expected number of times is simply 0.2, because that's the chance that it survives to breed once. And this is 0.6 for the bat. Whereas for the twice breeding ones, we have to figure out that, it could be that they managed to the first breeding attempt. And if they do, then there's another 20% probability applied to the mouse. So this second term is that it has to survive both to breed once and then to breed the second time, in which case it has bred another time. So we get 0.24 as an outcome. And you do the same sort of thing for the bat and you get 0.96. And you can see that the difference, both in terms of absolute numbers and in terms of the ratios, is bigger for the bat. So by how much did this expected lifetime reproductive success increase? For the mouse, it's a 20% improvement. For the bat, it's a 60% improvement if it managed to senesce more slowly. And it's actually not a coincidence that these are exactly the numbers that we put in there as the survival values. This can be shown that this is generally true. So it sounds like the bat is indeed more strongly selected to try to reap the benefits of a long life. And this is where the entire argumentation actually begins. So here some people say that no, this is too quick as a conclusion. Because the bat will also, all else being equal, and here we did assume that all else is equal, it will have a threefold population growth rate compared to the mouse, simply because at every stage of its life, it's surviving 3 times as well. And this is now about the extrinsic mortality, not about the senescence delaying abilities. And here in the corner, I've put this sort of little footnote saying that, of course, really, if you think about your intuition about mice, if you have them in your garden or whatever, they are actually able to grow extremely fast. They have high fecundity and so on. But all these fecundity differences, we so far just don't want to have them in the model yet. So this is really the bare bones comparison that we are making here. And just wait for a bit of a later minute in this talk when we admit that these kind of differences can be there as well. So this threefoldness maybe is just obvious to everyone, but if you do want to go through the actual way to prove this, you can make the Euler-Lotka equation approach, where we have the growth rate that we are trying to solve for. We have the proportion of individuals surviving to a particular age, and then we have the reproductive output of the survivors, and we didn't actually assume anything about them except that this is the same value for both species. So if we make that value equals f, age independent, then for the mouse to solve the population growth rate, we have this particular equation. For the bat, we have another equation. They look very similar, and you can solve them. And you can see that the only difference is that we have here a 3 for the bat and 1 for the mouse. So for this particular example, this really works. And it works for all other choices of numbers that you want to put in there as well. So if this high survival is allowed to translate into population dynamics without questioning what else might be going on in here, then we have a bat population that will expand much quicker than the mouse population. And in absolute terms, as time goes on, this difference grows very, very big. This is how exponential growth works. So here we can ask, what happens actually to the expected descendants that you get by placing an offspring into the population at a particular point in time? So if this particular bat managed to create an offspring here, then that offspring in itself will have some expected contribution to future generations, and that also expands. And if the bat survives, I've made the arrow a little bit paler now because there's only a certain chance that it's surviving to breed another time, then it will manage to create lineage of descendants where the expectation later is lower than the descendants of those that it managed to place into the population earlier. So this is a simple feature of exponential growth. You could think about it as the logical consequence of the fact that the population was smaller earlier. So if you manage to make one individual go into that population, then that individual forms a larger proportion of all the genotypes that are present, whereas later this one individual is a smaller proportion of, compared to all these competitors. And this expectation has consequences ever after. The same process works for the mice, but because the mouse population had lower survival, so everything is growing less well. So therefore, the difference is also less stark, what you get at the end. It's a bit hard to see here, but these are actually sort of mathematically precisely drawn curves. And this difference between the width of these two stripes here is smaller than the difference between the width of these two stripes here. So this is why people who say that, things don't actually matter, the extrinsic mortality doesn't matter. It's about the canceling out process that's going to go on. So here the bat is actually 3 times as likely to be able to put the second arrow into the population compared with what the mouse is doing. So I made this arrow now very pale to emphasize this point. The bat's late produced offspring are only 1/3 as valuable compared to the ratio calculation that you have to do with the mice. And because this 3 times and this 1/3, it cancels out. This is why people are arguing that extrinsic mortality shouldn't actually matter at all. And this is why we are so focused on population growth arguments in this field. So this trumpet shape, this exponential growth of the population, it really has an effect that it mathematically cancels out all the benefits that we are so used to arguing about, that, it should be easier for the bat to be strongly selected to live a long life because it can fly away from its predators. The trumpet might not actually be expanding forever. So this is where we enter the field of population regulation. And for those of you who don't think so often about population regulation, it goes back to the thought experiment involving Darwinian demons. What are Darwinian demons? This, amusingly, it's also a brainchild of George Williams. He's kind of like a hero of this talk. It's a hypothetical organism that matures immediately after birth, and it survives forever, and it has infinite fecundity. So it combines all the traits that natural selection is supposed to favor in life history evolution, and it manages to optimize, maximize everything that we want. So because nobody has ever found this creature in the wild, is very much about how you manage limited resources. And this is here just for 2 minutes. I'm just going to walk you through an example how I teach this subject to my undergrad students. So if you think, for example, about the ocean, then even back then when there was not so much whale hunting going on, when humans had not yet invented all these harpoons and things like that, if you just looked at a random bit of seawater, it probably didn't include a whale. You were lucky to be able to actually look at it and see a whale in there. But why? What actually regulates sperm population sizes? And for the students, I make this example where they need to calculate if exponential growth went on forever, how long would it take for you to be able to walk from Europe to the States just on the backs of whales, so that they would have replaced all the seawater? And this is how they have to approach this. They first have to figure out how big is a whale actually. And well, if you take a sperm whale, for example, it takes something like 20 cubic meters of volume, depends a bit on the sex. And then they have to be able to go online and figure out how much ocean do we actually have on this planet. And the depth is usually indicated in meters and the area is indicated in square kilometers. And they have to be able to convert this all into cubic meters, which most people manage after some head scratching. So this is actually the answer of how many cubic meters we have all the oceans. So we would need this many sperm whales to fill in all the oceans with absolutely no water left behind between them. This is quite a large number. But the point of the exercise really is that if we start from the current population size, which is something like 300,000 individuals, And if we had something like 3% population growth, which is much lower than for many of the smaller organisms on this planet, then try to form an intuition, like how long would it take before there really is no water left between them? And of course, in reality, this cannot happen because, where would the carbon even come from and so on. But the point is to get an intuition for how efficient exponential growth is. And the answer is it's something like 800 years. So very, very rapidly this would happen. And in reality, of course, whale-like things have existed for an incredible number of years. They were a bit less whale-like looking 40 million years ago, but from here onwards, they have been there. And obviously they haven't replaced the seawater. So what happens if you look at the ecology of whale reproduction, there's evidence, for example, that if the feeding gets not so good and the blubber in the females gets thinner, then the pregnancy rates start dropping so that the reproduction actually becomes impossible quite quickly. And that's how populations can get regulated. And this is why the debate where this R equals 0 appeared in the debates. So we expect the trumpet shapes not to go on forever. We expect there to be something like a relatively flat population over time. So if we switch from this scenario where the bat is 3 times as likely to create an extra offspring compared to the mouse, but it's only 1/3 worth it, it's now 3 times as likely to create that extra offspring. And now it's totally worth it because there's no penalty when it comes to the later representation in the population, whether you put your offspring in there earlier or later. So here it looks like William's argument can be valid because the bat advantage as a net effect was rescued. But here it's again the next step in this debate. Is it actually okay to assume that the bat kept its 3 times as high survival intact now that we also assume that its population cannot grow? Because population growth rate is not something that just sort of can be put in as an external parameter into a model. You just sort of don't use a dial where you just put the R value into being high or low, because it should emerge from the dynamics that you're assuming what happens to the individuals. So if the population growth rate goes down, something should change in the lives of organisms that form the population. So some existing individuals should die at a higher rate, or maybe they reproduce less well. And this actually matters a lot, because maybe the adult bat does reproduce less well, and that means that it might actually still survive really well, but the population is not growing. Or it might be that the population is not growing because so many of the adults are dying. So this finally then also gives us the opportunity to remember that the fecundities do differ between the bats and the mice. So therefore, let's finally stop this silly assumption that fecundities are always the same between different organisms and go to this idea of fast and slow life histories. And the fast one here is assumed to kind of accept that it's going to senesce at an earlier age. We can vary the model as in kind of like exactly at what age it will start descending towards its 0 survivorship values. And we assume a particular Gompertz-Makeham shape of mortalities. We have also replicated this with another shape, so that doesn't matter so much. But the fast one, it has then the advantage that it's producing more offspring per breeding attempt. So this is like the mouse style thing. The slow ones, on the other hand, there we assume that they reproduce less per breeding attempt, but they avoid senescence completely. So they will follow this exponentially decaying probability of being alive after a certain number of time units have passed since birth. So effectively, they are the ones that have bought these ugly shoes that I was mentioning before. And we are going to ask 3 questions here. Remember, we assumed that there's a difference in fecundity between the 2 types. How big should this fecundity difference be for the fast one that dies earlier to outcompete the slow one. And the second question is, does this threshold depend on extrinsic mortality? This is basically the Williams hypothesis question. And the third question is whether the answer to the second question depends on how the populations are regulated. So all of these questions, they get their answers in the kind of like same figure that I'm going to show you, where on the x-axis, we have extrinsic mortality that ranges from a low value to a high value. And then on the y-axis, we have the relative fecundity of the slow type, where unity would mean that it's equally good as the fast type. And of course, if it's equally good as the fast type, then the answer is kind of trivial. The slow should beat fast. It's a better thing because fecundities are no different, but slow lives longer. And if slow has zero fecundity, then obviously it will not have evolutionary success either. So therefore, there must be a threshold in between where the fate of the outcome flips between favoring one to favoring the other. So it could be, for example, that is a flat line. And if it's a flat line, then, well, the answer to the question number one is that, well, that's the required ratio. Question number two is that there's no effect of extrinsic mortality, so that Williams was not correct with this hypothesis. And question number three, which was about population regulation, is whether this flatness is there for all possible shapes of population regulation, or maybe there's some type that creates another shape. So it could also be that the picture looks like this, so that at high extrinsic mortality, there's much more scope for the fast life history to evolve, and much less for the slow, because the slow must have a really high fecundity for it to be still favored. This would be a case where Williams' hypothesis holds. And then we also asked, is it possible that, maybe there could be something that we could call anti-Williams? So not only is there, or it's not like there's no relationship, but it could be that, the relationship actually goes in the exact opposite way that he was presenting. So this is a picture of Williams turning in his grave, having thought of that. So the results, I will just sort of make them all appear at once, but I will just prepare you a little bit for what's coming. We have here, there will be a total of kind of like 10 different cases where we have regulated a hypothetical population in different ways. We can have age-independent survival, being impacted by density dependence, maybe in a continuously strengthening fashion, so that if the population gets more dense, then everybody has a harder time surviving. Or it could be that it's probabilistic, that exponential growth can keep going until the population is really dense, and then some disease goes through the entire population and only some of them survive. Or it could be deterministic, that once you reach a certain cap, then this disease happens. Similar things could happen, but this time they could impact mostly adult survival, or they could impact what happens to the juveniles. So maybe the juveniles are the ones who are more prone to dying, or maybe they are never produced. And we also include this sort of extra category here for the competition for territories, because this is something that tends to impact juveniles, that if all the adults have their breeding territories already, and the juveniles cannot recruit into the population unless an adult has died, this is a form of population regulation that keeps populations near the carrying capacity very well. But we also only did it for this last category because this is how things typically work in things like territorial birds. So remember what I said, if we find flat lines, that's when we have the null. So this is where Williams is wrong in a null kind of sense, that there's no effect of extrinsic mortality. If we get a declining threshold, then we have found the anti-Williams. And if we find increases, then we have found the Williams to be true. And this is, as you can already see, we can find all kinds of things happening in here, but not without logic. You can see that the solutions, they always line very nicely with what we are assuming about who is actually suffering when the densities get higher. And Williams ends up being supported in those cases where higher population densities really make life tough for juveniles. And if it did the opposite, if it was the adults, those who are actually responsible for the breeding, if we started killing organisms from the oldest ages classes, moving downwards, then we would actually find the cases that align with the anti-Williams ideas. And the cancelling out effect, it's fully showing its potential to impact the solutions in this upper case where there's no difference in how old you are, how extrinsic mortality is impacting you. So this is all published, and I think that if there's just sort of one sentence I would like to highlight from this talk, or from this way we wrote it up, is that empiricists have found the Williams type pattern very intuitive. They have also found quite a lot of evidence for it in natural populations, and this to us seems to indicate that maybe if I go back to this, maybe it really is quite a common finding in nature that when the going gets tough, it tends to be the youngest age classes who really have a rough time getting into the population. This is the conclusion from here. But the other thing that I would like to maybe mention, I put the journal name here really quite big, and that's the reason that it's a very new journal, and it's one of those where you know how we're sort of trying to make scientific publishing something that makes sense to scientists, instead of having ever increasing costs going to the pockets of those who own the journals and the stakeholders and things like that. This is an initiative where a while ago there was actually a pledge that people should send their best work to this journal or its sister, or the same journal but different sections. Like you saw here, there's the section evolutionary biology. There's also sections like ecology. And we actually, I said, I did put my name in there that I will do this. And by now I have 2 papers in here. The other one is a completely different story. It's about Wolbachia, which is a bacterium that impacts insects. And therefore, if you sort of believe in these kind of things being good, then I would kind of, try to make these journals well known. You can try to send something in there. You can, if you manage to cite both the Wolbachia paper and this paper in one of your papers simultaneously, then I will totally buy you a beer, because I have no idea how they would link with each other. But I think with that, I'm basically done. And I hope you enjoyed this. I hope that the audio actually worked, because there was a crazy storm coming through, and because I'm on mobile internet, this may have caused some trouble. I don't know how it came out at your end, but thanks for listening.
Thank you so much, Hanna. The audio was okay enough, I think, for the recording, although it did have episodes, let's put it this way. But I think people can reconstruct what was going on. So thank you again so much for the talk. And if anyone has questions, please raise your hand in the participant list. Questions?
Hey, yeah, sorry about that. Yeah. Okay, I'm sorry. Yeah.
Sorry? Any questions? Just a second. Where did Hanna go?
Sorry, Zoom kicked me out briefly, and then sorry about the there really is a storm light on that. That creates trouble.
No, no worries at all. And Mike has a question, so please go ahead.
Hi, Anna. Nice to hear you talk. Thank you very much for that. Just
Hello.
just a quick question about these three different scenarios that you raised at the end. Are they mutually exclusive? Can we have different combinations of different parts of those scenarios? How do these link in together?
Yeah, so well, there were three different rows, but there was actually 10 completely independent scenarios in there. Right. And yes, they could combine in different ways, and we have actually played with a few combinations. So, for example, it could be that let's consider the scenario where a disease comes through a population. As we know, sometimes it could be that both infants and really old individuals might be the ones who are susceptible. And then if you do play with those kind of cases, then maybe as intuition would expect, make you expect, you will find that you can get a bit sort of more variation in the patterns with extrinsic mortality. So yes, we were actually thinking about whether we should put that into the paper as well, but then we felt like, oh, this was already quite a sort of story. So maybe that extension would have been just sort of so intuitive that in the end we kind of voted to leave it out.
Cool, thank you.
Thank you very much. If there are more questions, oh yeah, Sarah, please go ahead.
Hi, thank you for that. I unfortunately came in just a little bit late, so if my question was something that was covered before I jumped in, I apologize ahead of time. Mm-hmm. I love this. I love the idea of not looking at this statically, but more dynamically. And I'm interested in what you think the sensitivity might be for organisms at the extremes of sort of the standard life history framework. So very fast living, short lifespan organisms versus long-lived organisms like a chimpanzee or an elephant, and how sensitive they are to these sort of temporal changes.
Well, I think I was maybe a little bit cheeky here when I showed the picture of the killifish, because one thing that we didn't consider is a sort of very strict seasonality that might form a constraint to lifespan, where you really cannot go over, once it's 10 months into the season, then the things are going to end. And of course, you need to have all the maturation process and everything having happened and completed before that. So many of the extremes, I think they relate to ephemeral resources, where you just sort of have to schedule your life obviously quite differently if you cannot even survive in an adult form through it. And when it comes to elephants and the other extreme, I think they would actually be more or less covered by our model, because they just live at the very low end of the extrinsic mortality spectrum. That said, we didn't actually include anything like an explicit longer juvenile period, which also happens in many of these organisms, so that if the entire pace, what's often called pace of life, is slower, then you might also need a longer time to grow big enough to experience all these adult mortalities and so on. So that can, for individual taxa, there's a lot of taxon-specific things that you probably would have to take into account, or insects that are metamorphosing, or you name it. But hopefully it was inspiring enough the way it was.
Thank you. Yes, it was.
No, thanks.
Agreed. Thank you. Are there any other questions? While people are thinking, I might have a one that possibly overlaps with Mike's earlier question, which is that it would seem that in reality, it's neither juvenile or senesced individuals, but both, right? That actually organisms are initially vulnerable, then they get into the prime of their lives and they're essentially invulnerable to any sort of predation or problems, and then they get vulnerable again. So
yes, but there's actually a bit of a twist here. So it's not just the absolute death rate that is for example, for humans, it's U-shaped, that it's a bit bigger for infants. And if you live in developing countries, it's much bigger. And then it rises steeply at the end. It's about the responses of how that curve changes when density gets higher.
Okay.
So and that can be quite system specific. So if you have, for example, like my example of the territorial birds, the tough life really impacts those that don't have the territory. And even if the density is higher, if it just means that the so-called floaters that get more common, they are the ones who are homeless, so to say. The adults who have a territory, they might actually not be impacted so particularly well, or particularly much. So these are the kind of processes, and unfortunately, they're harder to measure than just the raw data on mortalities. But that's why, like I said, I wanted to just talk about one paper for 45 minutes or whatever it took, just because already without these complications, it's a fairly complex story.
Thank you. Yes. Yes. Any other questions? No, it seems there are no more questions.
Well, if everyone is happy, then I'm very glad.
Changes their mind. Here's the last chance. No, well, all right. I guess it was so clear, but nobody has any questions.
Okay. Thank you so much.
Thank you so much, Hanna, for coming. And thank you everybody else for coming as well. We will be in touch soon about the next seminar and hope to see you all there. So thank you again for coming and see you next time. Bye, everyone.